So in today's video, we're going to go ahead and see how we can use integration by parts to evaluate definite integrals. And so really what we're going to come to find is essentially just the same thing as regular integration by parts. The only difference is we just evaluate our antiderivative at the end at the two endpoints as we would, for any other definite integral. And so let's just go ahead and do a couple of examples here to illustrate what I mean by that. So here we have the integral from 1 to e squared of x squared natural log of x dx. And I've written the integration by parts formula up here, just the general one for the indefinite integral. But if you wanted this to be for the definite integral, then you'd essentially just have your two bounds of integration, and really you just evaluate the entire expression at those two bounds. And so let's go ahead and actually see how that applies to this particular case. So first of all, we want to define our u prime and our v. And looking at these two, like the product of these two functions, we have x squared and we have natural log of x. And there aren't really any functions, at least off the top of my mind, that have an easy derivative equal to natural log of x. There's no easy or obvious functions that have a derivative of natural log of x, but there are for x squared. We know that if we let u prime equal to x squared, we know that u is just equal to x cubed over 3, right? Because we take this derivative, you'll just end up with x squared. So it's a very easy kind of function it's very easy derivative of a function. Meanwhile, natural log of x, we can just let that equal to v. We can let v equal natural log of x, and we know that v prime will just be equal to 1 over x. And so then with that in mind, we can go ahead and just put these into our formula. So let's go ahead and do that. So here we have u times v, which is going to be x cubed over 3 natural log of x. Then we're going to subtract that from the integral of v prime u. V prime u here is just going to be x cubed over 3 times 1 over x, which is just x cubed over 3x dx. But then over here we have x cubed over 3x. That's just going to become x squared over 3 dx. And then at the end we can just put these brackets over here. We're going to evaluate it at these two endpoints. So from 1 to e squared. And so let's go ahead and continue. This right over here, x squared over 3, we can first of all write out x cubed over 3 natural log of x. And then this right over here, x squared over 3, if we just use the reverse power rule, we'll end up with minus x cubed over 9. And then we're evaluating that at these two endpoints, so from e squared to 1. And then we can just go ahead and input these two different values. So when we input e squared, we end up with e to the 6, right, because it's e cubed squared, over 3 natural log of e squared minus e to the 6 again over 9 over here, e to the 6 over 9, and then we're going to go ahead and just subtract all of that from this evaluated at 1. That's x cubed over 3, that's just 1 over 3 times natural log of 1, which is just 0, so that disappears, and then minus 1 over 9. So let's go ahead and do some simplification here. We know that natural log of e squared is just 2 over 3 e to the 6 minus e to the 6 over 9. Let me fix that. E to the 6 over 9. And then this is just going to be plus 1 over 9. And so then ultimately over here, we'll just end up with what this is going to be. 2 over 3 e to the 6 is just 6 over 9 minus 5 over 9, so that's, or minus 1 over 9 is just 5 over 9 e to the 6, and then plus 1 over 9. That right over there would be our final answer. And so really all it is just using integration by parts and then evaluating it at the two endpoints at the end. Keep in mind that also you could just evaluate this first portion over here at the two endpoints, then subtract it from the definite integral from 1 to e squared of x squared over 3. Both of these will get you the same answer. It's whichever you prefer. But here we just did this particular method. And so next up, we're going to be evaluating the definite integral from 0 to 1 of arcsine of x dx. And so again, like we did in the first video, when we have something that's just appears to not really be the product of two functions, here it just looks like it's arcsine of x, we always have to remember that there's an implicit 1 over here. We know that this is just 1 times arcsine of x, and then that will help us when we want to integrate by parts. And so there's no obvious function that has a derivative of arcsine of x, but we do know that if we let u prime equal to 1, then u is just equal to x. So it's a very simple sort of kind of definition of u over here. And then we can just let v equal to arcsine of x such that v prime will be equal to 1 over the square root of 1 minus x squared. and then we can just go ahead and proceed. So now we just need to go ahead and put this into the formula. We get u times v, which is x arcsine of x. And then we're going to subtract that from the integral. We could define this, put the bounds of integration here. We can just put it at the very end. It doesn't really matter. The integral of this is going to be now x over the square root of 1 minus x squared, right? Because this is just going to be u times v prime dx. And then we can just go ahead and integrate. So, I mean, of course, we have the bounds of integration. This is from 0 to 1. And over here, we can use a u substitution, or if you want a different variable, we can make like a w substitution, we can say. So if we let w equal to 1 minus x squared, then w, or dw, will be equal to negative 2x dx. And then we can just go ahead and manipulate this a little bit. So we can bring this negative sign inside. We can put a 1/2 out here, so this becomes a negative 2x. And then we can just integrate. So this will be equal to 1/2 times the integral of negative 2x dx, we said it's just dw, right? And then over the square root of 1 minus x squared, that's just the square root of w. If we want to bring the 2 inside, actually, that could also be beneficial. We'll end up with square root of w. This is ultimately just square root of w, which is square root of 1 minus x squared. So this is just some simple substitution over here to evaluate this integral. And so then finally, our antiderivative here is just going to be x arcsine of x. Or actually here it's going to be plus the square root of 1 minus x squared. And we're evaluating this from 0 to 1. And so when we evaluate this at 1, that's just going to be 1 times arcsine of 1, which is pi over 2, right? And then plus the square root of 1 minus 1 squared, so that's just going to be 0. And then we're going to subtract that from here, x arcsine of x. When we evaluate that at 0, it's just going to be 0 arcsine of 0, so it's just 0, plus the square root of 1 minus 0 squared is just 1. And so our final answer is going to be pi over 2 minus 1. And that right over there is our definite integral evaluated. And so really all that it is just taking the antiderivative using, or finding the antiderivative using regular integration by parts, and then at the very end you just integrate as you would a definite integral. Just like as you would evaluate a definite integral, you just need to put in the 2 bounds of integration, subtract them, and that's how you'll end up with your final answer over there. And so I hope this helps, and I hope it's not too confusing.